The purpose of this demonstration is to provide you with an introduction into how an Autodesk Intent application is created. In this demonstration, we will cover how Inventor parts and assemblies can be adapted to Intent objects, an overview of the Intent developer environment and concepts, how to add attributes and expressions to an Intent object, adding Intent parts to an assembly, using Intent to drive the position and orientation of the Inventor parts, adding an existing subassembly to an Intent assembly, and Intent configuration rules. The example we will be building is a conveyor support. It will have two legs, which are pre-built Inventor parts. The support will also have a lateral support positioned between the two leg supports, which will be configured according to the load on the support. The support input parameters will be length, width, height, and load. The first step in the process is to adopt an Inventor part to an Intent object. Intent is able to take full advantage of existing Inventor parts and assemblies and use rules to drive their location, orientation, parameterization, and configuration. Assembly adoption is not shown in this demonstration. The part we are adopting is a leg object. We will first scan through the leg part and see that it is made up of two extrusions and a fillet. The Inventor part has also been supplemented with a series of work planes and work points that provide easy handles for Intent to utilize in positioning and orienting the part. We will be using the left, right, longitudinal, and top work planes in our example. Next, we will look at the Inventor parameters and notice that there are 6 primary parameters that have been given user names, including the length, width, and height of the leg. We use the browser bar pull-down menu to change to the Intent view and select Adopt. This brings up the Intent Adoption Wizard, which shows the parts that are eligible for adoption. We can then look at the parameters that will be adopted to Intent object attributes. After the adoption process, there will be an Intent object that can create and drive the Inventor part using these parameters. Note that by default, only the user-defined parameters are adopted as attributes, but this can be modified by the user. Once complete, the new Intent part is saved. The next step in the process is to open a new Intent project. We will name our project Quick Support and declare it as an assembly. This process also opens up the Intent developer environment. The 3 parts of Intent developer are the library of objects and functions, the assembly tree, and the editor. Intent applications are built by utilizing the library of existing objects to build new objects and assemblies. As each object is added, you can also add attributes to those objects. These attributes are like the cells of a spreadsheet. They have an expression that defines their relationship to other attributes of that part and other parts in the assembly. For example, a spreadsheet expression in column C can define that the value of that cell is the sum of column A and B. The spreadsheet will keep track of that declared relationship. Intent implements that same functionality but extends it into the engineering world by enabling geometric and spatial relationships, engineering relationships, and rules-driven configuration relationships, resulting in a powerful system for automating engineering and design processes. Let's begin defining our quick support by adding the input parameters length, width, height, and load. This is done by executing the Add Attribute command, selecting the parameter box, and then supplying a default value for each. Our defaults are length 50. This defines the length of the support along the conveyor direction in millimeters. Width 300, height 700, and load 80. The next step in the process is to add subassemblies to our quick support design. We will do this by looking in our project library to find our adopted parts. We can drag and drop the leg part to the quick support and it will be added as a child. We will give this instance the name of leg left. We can see that the adopted leg part indeed does have attributes that correspond to the parameters of the Inventor leg. We will define the length of the leg to be the same as the length of the quick support. We do this by editing the length attribute of the leg and then selecting the quick support length attribute with the mouse. This will automatically create the appropriate reference from the leg to the quick support length attribute. This is a simple reference, but other more complex references can be created in the same way. We will also define the height of the leg as the height of the quick support. Note that we are creating simple expressions that define the behavior of the leg. These expressions can contain mathematical relationships, like in a spreadsheet, logical if-then relationships, engineering rules, calls to external programs using a remote function calling facility, and references into databases using ODBC. We can now see that Inventor has created the leg model with the appropriate parameters. Next, we will add a second leg, leg right, using the add similar child command. We will also need one calculated attribute. We will add it to the root quick support object and call it distance between legs, and define it as the overall width of the support minus the leg left length and the leg right length. Now we need to position and orient the legs relative to one another. We will do this using mates that are driven by a part-to-part mate design from intent. The part-to-part mate design takes the parameters necessary to define the relationship between two parts in 3 axes. It will create and drive Inventor mates in the similar way that the leg part creates and drives the leg Inventor part. We will name this part leg-to-leg mate. It will drive the position of leg left as part 1 relative to leg right as part 2. We will define the lateral offset to be the distance between legs and allow the longitudinal and vertical offsets to default to 0. Next, we need to define the entities on each part that will be mated. We will use the right longitudinal and top work planes of the left leg and the left longitudinal and top work planes of the right leg. Finally, we will define each mate solution. In this case, the lateral mate has a mate type solution and the longitudinal and horizontal will be flush mates. Note that the part-to-part mate object automatically created 3 individual mate objects. Also note that the legs have been correctly positioned relative to one another, and you can see that the entire Inventor assembly with subassemblies, parts, and mates has been automatically created. Now we will add a tie beam set subassembly that has been previously created. We will call it lateral support and give it a height that is 1/3 of the height of the support, a length that is the same as the support length, and a width that is the distance between legs. The tie beam set was designed generically to fit into a boxed shape that you can see as a glassed outline. This boxed space is used to generically position and orient the assembly. We can see that the new assembly has been added but not positioned and oriented. We will position and orient the tie beam set using another part-to-part mate. This time, part 1 will be the leg left, and part 2 will be the bounding block of the tie beam set. We'll align the components on their longitudinal axes and mate them at the top. We will use the default offsets of 0 except for the vertical offset, which will be set at 1/3 of the support height. When we look at the graphics, we realize that the vertical offset actually needs to be in the negative direction. This is a good example of the debugging power of automation rules in a graphical environment. The graphics provide immediate feedback about the correctness of the rules. Now we see that the lateral support is positioned properly. Finally, we will look more closely at the lateral support. Note that the design or type of the support is a tie beam set. The type of an assembly can be determined from a rule, just like all other attributes. Note also that each node of the tree can have a rule about its subassemblies, so that quite sophisticated configurable assemblies can be created. In this case, we will define a rule that selects between the tie beam set and the cross brace set based on the load on the support. A heavier load will require the more expensive cross brace set. Otherwise, we can use the tie beam set. This is an example of a simple engineering rule driving the configuration of the assembly. Since the default load was 80, we can see that the configuration is not changed as of yet. Now we will change the quick support parameters so that the load is 150, the height is 500, and the width is 500. Note that the intent assembly tree has changed significantly. Also, the Inventor model has changed significantly. The subassemblies, parts, and mates have all updated appropriately to create the new support. Note that the Inventor assembly is not simply turning on and off parts. The configuration of the Inventor assembly is actually changing. In a matter of minutes, we have created an automated design. Notice that I can create very different geometry, any number of completely different assembly configurations, without noting a priori what those combinations are or even how many of them there might be. This quick support demonstration has given you a brief introduction to how Intent works with Inventor, how Intent attributes are created, and how Intent assemblies are created. We have also seen positioning, orientation, and configuration rules. From here, an application can be used as is as an effective implementation of custom functional design, in this case automating the functional design of a simple support. It is also possible to create a deployable application by adding a custom user interface, driving the component level and assembly drawings associated with the design from Intent, and generating custom Word and Excel documents such as bills of materials, quotes, and proposal documents. These applications can then be deployed to less technical, non-Inventor users, such as application engineers, salespeople, or even customers. Intent automation applications can be used to dramatically increase the effectiveness of sales personnel and increase the efficiency of order engineering. Thank you.